Are we alone? Is there life beyond Earth? Despite being among the most profound questions humanity has ever asked, they remain unanswered. Even the smallest piece of evidence, something as simple as a single microorganism found in the atmosphere of another planet, would force us to completely rethink our understanding of life and our place in the universe. That is why, in the vast and seemingly endless darkness of space, we spend billions of dollars sending probes and spacecraft across the solar system, searching for even the faintest sign that we may not be alone. Today, this search is no longer limited to our own cosmic neighborhood. We're now capable of investigating planets orbiting stars tens or even hundreds of light years away. But how is this possible? If exploring planets within our own solar system requires enormous resources and still leaves us with limited knowledge, how can we speak so confidently about the atmospheres and potential habitability of worlds far beyond it? Since 1995, astronomy has entered a new era with the study of exoplanets, planets that orbit stars outside our solar system. Over the past 3 decades, astronomers have confirmed the existence of more than 5,800 exoplanets, revealing an astonishing diversity in size, mass, and composition. Each of these worlds represents a unique possibility when it comes to habitability. Recently, one particular discovery reignited global debate about extraterrestrial life. An observation involving an exoplanet located approximately 124 light-years from Earth, known as K2-18b. The story began in 2023, when the James Webb Space Telescope detected carbon dioxide and methane in the atmosphere of K2-18b. The presence of these gases, combined with unusually low levels of ammonia, suggested an atmosphere rich in hydrogen and hinted at the possibility of a vast global ocean beneath. Because of these characteristics, scientists classified K2-18b as a Hyson world, a term formed from hydrogen and ocean. But the most intriguing finding came next. Webb's data also hinted at the presence of dimethyl sulfide, DMS, a molecule that, on Earth, is primarily produced by living organisms, especially marine phytoplankton. This immediately raised a provocative question. Could this be the strongest evidence yet for life beyond Earth? At a distance of 124 light-years, the light we observe from K2-18b today actually left the planet in the late 19th century. Sending a spacecraft there is completely unrealistic. Everything we know about this world comes from analysing its light. Astronomers use a technique called the transit method. When an exoplanet passes in front of its host star, it causes a tiny dip in the star's brightness. More importantly, some of the starlight filters through the planet's atmosphere during this transit. Different molecules absorb specific wavelengths of light, leaving behind a unique pattern, like a barcode or fingerprint in the star's spectrum. This process, known as transit spectroscopy, allows scientists to identify the chemical makeup of distant planetary atmospheres. This is how molecules such as methane, carbon dioxide, and potentially dimethyl sulfide were detected around K2-18b. Despite the excitement, the answer to whether this proves the existence of life is still no. K2-18b orbits a red dwarf star, a small and relatively cool type of star that makes up roughly 80% of stars in the Milky Way. Because red dwarfs are dim, their habitable zones lie very close to the star. K2-18b completes an orbit in just 33 Earth days, yet still falls within the region where liquid water could exist. While this makes red dwarf systems appealing targets for life searches, they also come with challenges. These stars are highly active, prone to flares and surface irregularities that can distort spectral data and produce misleading signals. This uncertainty has divided the scientific community. Initially, the DMS detection reached a 2 sigma confidence level, meaning there was a 5% chance the signal was a statistical fluke. New observations improved this to 3 sigma, reducing that probability to about 0.3%. However, in physics and astronomy, 5 sigma is typically required for a definitive claim. Even more importantly, these confidence levels depend heavily on the accuracy of the models used. If the model itself is incomplete or flawed, the conclusions may still be wrong. But this brings us to the million-dollar question. Is dimethyl sulfide truly the holy grail of biosignatures? On Earth, the answer would be a simple yes. Here, DMS is unmistakably the scent of life, produced almost exclusively by phytoplankton in our oceans. But in the cold, chaotic vacuum of space, the story gets much more complicated. Even if the presence of DMS is confirmed on K2-18b, its interpretation remains a battlefield for astronomers. Skeptics argue that we might be jumping to conclusions. Advanced laboratory simulations have thrown a wrench into the alien life theory. They have demonstrated that under the harsh glare of ultraviolet radiation, simple organic ices can undergo complex chemical reactions to synthesize DMS, completely without the involvement of biology. This isn't just theoretical speculation. In fact, the universe has already shown us that it can produce this molecule in dead environments. The Rosetta mission made a startling discovery on Comet 67P, a frozen rock tumbling through the dark void. It detected traces of DMS. Since comets are sterilized by deep space radiation and lack active ecosystems, this proves that nature has non-biological pathways to create this specific molecule. Similar traces have even been found in vast, freezing interstellar gas clouds. These findings challenge the idea that DMS is a definitive smoking gun for life. However, the research team behind the K2-18b observations isn't backing down. Their counterargument relies on one crucial factor: volume. While a comet might produce a faint trace of DMS through random chemistry, life acts like a planetary factory, pumping out massive, continuous quantities. The signal detected from K2-18b suggests an abundance that current abiotic models simply cannot explain. So, are we looking at a thriving alien ocean teeming with microbial life? Or have we stumbled upon a new, exotic form of atmospheric photochemistry that merely mimics the signature of biology? For now, the door remains open, and the universe is making us work hard for the answer. At present, declaring the discovery of alien life on K2-18b would be scientifically irresponsible. The signals are there, but they are faint, and the origins are hotly debated. However, the final word hasn't been spoken. The James Webb Space Telescope is scheduled for follow-up observations using its MIRI instrument. These upcoming scans are critical. They won't just look for DMS again, they will hunt for corroborating evidence, specifically analysing methane and ammonia ratios to confirm if a liquid ocean actually exists beneath those clouds, or if this is just a lifeless gas dwarf. That is the true marvel here. Just 30 years ago, we didn't even know if planets existed beyond our solar system. Today we aren't just finding them, we're dissecting their atmospheres trillions of kilometers away. Whether K2-18b turns out to be a living world or a silent sub-Neptune, the data we gather is rewriting our understanding of the cosmos. As exciting as the headlines are, real progress requires patience. Until next time, we'll continue our search in another distant corner of the universe,